Hello everyone. In the previous video, we studied about the center tap full wave rectifier, where the center tap full wave rectifier used a center tap transformer in which the load resistance was connected across the center of the secondary winding of the transformer, and we used two diodes. During the positive half cycle of it, only diode D1 was conducting and diode D2 was not conducting. Similarly, when we went for the negative half cycle, the diode D1 was not conducting, that is, it was in the reverse bias, and my diode D2 was in the forward bias condition. As a result, I could see the conversion of AC voltage happening both in the positive as well as the negative cycle. Now, after this, we also studied the derivation or the expressions for the average or DC voltage and current, that is given by IDC or I average is equal to 2Im by pi, and VDC or V average is given by 2Vm by pi. Similarly, we also derived an expression for the IRMS value and the VRMS value. For the IRMS value, we got Im by root 2, and for the VRMS value, we got Vm by root 2. Similarly, we also derived an expression for its efficiency, wherein which it proved the efficiency of the full wave rectifier is more compared to the efficiency of the half wave rectifier. In the full wave rectifier, whether it could be a center tap rectifier or the bridge rectifier, which we are going to study in this video, the efficiency is going to be the same. That is, we got the efficiency of the full wave center tap rectifier as 81.81%, and the ripple factor is equal to 0.408, right? So this is what we studied in the previous video. Coming to the bridge wave rectifier, we had some of the drawbacks in the center tap full wave rectifier. The disadvantages of center tap full wave rectifier are here, since we are using two diodes, since we are using two diodes, whatever, we must have the diodes, that is, in the previous half wave rectifier we used only a single diode, but for the center tap rectifier we use two diodes. These diodes must have high peak inverse voltage, and the another disadvantage is each diode we use will have only one half cycle of the transformer's secondary voltage, the DC output, is comparatively small. So this was a drawback for the center tap rectifier, which led into the foundation or into the study of bridge wave rectifiers. So we can see here the bridge wave rectifier is going to incorporate, as usual, with a transformer. The primary winding of the transformer is given with the supply voltage, and the secondary winding of the transformer, when the primary winding of the voltage, when the primary voltage is applied to the when the voltage is applied to the primary winding of the transformer, the secondary voltage, the voltage across the secondary winding is going to be through your primary winding. So when we look into the graph, the waveforms during the positive half cycle of the input, that is represented as Vs, the input is represented as Vs. During the positive half cycle of the input, that is from 0 to pi, the diodes, that is we use actually in the bridge wave rectifier 4 diodes. The connection of the diodes are done in such a way that the polarities are very much important when we connect the bridge wave rectifier. So once we use a 4 diode and when we give the positive half cycle as its input, now the diodes which are opposite, that is D1 and D3, that is we can look through the polarities across. The polarities across the point, let me name this point as A or the node as A and node this was B. Now once the positive cycle is applied here, I can say the polarities across this, the secondary winding is going to be positive and negative, and it is as shown here. Now once this is going to become positive, point A is positive now, can I not say my diode D1 is now in the forward bias condition? Look into the diode D2. Is it in the forward bias? No, this is because it is a reverse bias. Now look into D3. My cathode is connected to the negative terminal, so I can say my D3 is forward biased. So my diode D1 and D3 are forward biased, whereas my diode D2 and D4 are reverse biased. So I can say during the positive half cycle, my diode D1 and D3 is on and my diode D4 and D2 are off. Similarly, when we go for the negative half cycle, of the input, I can say, that is when I give a negative half cycle as my input, I can say the polarities across the secondary winding of the transformer is negative, positive. Now what is going to happen? My diode D1 is now in the reverse bias condition according to the polarities, and my diode D2 is now in the forward bias condition. Similarly, what is going to happen with respect to D3? Because this is a positive terminal, I can say my diode D3 is in the reverse bias condition and my diode D4 is in the forward biased condition. So during the negative half cycle of the input, I can see my diodes D2 and D4 are forward biased and it is going to act as a closed path. That is, if I represent this during the positive half cycle, I can say my diode D4 is a open circuit, my diode D1 is a closed circuit, so continuous. Similarly, my diode D2 is a open circuit and my diode D3 is a closed circuit. So this is my D1, D2 and D3. This is how my circuit is going to be during the positive half cycle, and during the negative half cycle vice versa. This is going to become closed switch and these two are open switch. So the inference that we are going to get from the bridge wave rectifier working principle is, during the positive half cycle, the two diodes are going to conduct, and during the negative half cycle, the opposite two diodes are going to conduct, right? So as a result, I can expect both at the positive as well as the negative inputs, waveforms. I can expect the conversion of AC into DC waveforms, right? Now coming to the um, uh, average voltage and average currents, that is whether it could be average current or DC current, we call one and the same. So when we come for the IDC or I average, I can say the very same expression holds good for the bridge wave rectifiers, that is IDC is equal to 2Im by pi, right? So the very same expression holds good for your bridge wave rectifier also. Similarly, when I go for the VDC, this is also equal to 2Vm by pi. Similarly, when we go for the IRMS value, My IRMS value is also equal to Im by root 2 as in the center tap rectifier, and my VRMS value is also equal to Vm by root 2. But the only thing that we are going to vary in the efficiency as well as the ripple factor is we are going to replace the RF resistor with, wherever we find the RF resistor, we are going to replace it with 2RF. So no matter whatever could be my the same step holds good, but the only thing there is a variation is we are going to substitute wherever we find RF into 2RF, right? So this is what, so when we come for the efficiency, the very same efficiency, this is also going to provide you 81%. And similarly, when we come for the ripple factor, that is gamma is equal to 0.40. So there is no difference when we use a bridge wave rectifier or a center tap rectifier. Because of the drawback of the center tap rectifier, we are into the bridge wave rectifier. That is, the drawback was the diodes used must have the high peak inverse voltage, right? So as a result, we are into the bridge wave rectifier. Now, we know everything is same, but even the bridge wave rectifier is going to find or is going to have some drawback. Now, what is the drawback? I can say in my bridge wave rectifier, I can find 4 diodes, right? So there is a presence of 4 diodes, wherein which, since there is a presence of 4 diodes, I can say there is a more number of power dissipation happening, right? Power dissipation is more in case of bridge wave rectifiers. Okay. Now, in order to conclude the rectifiers part, let us look into this chart where this gives you a relation for various kinds of rectifiers with its parameters that we have derived. Okay. Now, when we come for the IRMS, that is RMS load current, for the half wave rectifier, let me name this as half wave rectifier HW, and this as a center tap full wave rectifier CFW, and this as a bridge rectifier, so BR. So when we look into this, my IRMS or the IRMS load current is equal to Im by 2 for the half wave rectifier, and for the center tap full wave rectifier it is Im by root 2, and for the bridge wave rectifier it is Im by root 2. And when we come for the VRMS, that is RMS load voltage, we have Vm by 2, Vm by root 2 as my center tap rectifier, full wave rectifier, and for the bridge rectifier it is Vm by root 2. Similarly, when we go for the power conversion efficiency, which is given by eta, that is efficiency, it is given by, for the half wave rectifier it is only 0.406. In order to show you the difference where you have to substitute 2RF, it is written in this form, or else you would have directly written it as 0.406. And when we come for the center tap full wave rectifier, I can say the efficiency eta is equal to 0.812%, and for the bridge wave rectifier, you can see the difference here. The substitution of 2RF is very well shown for this expression. So this is what you have to do whenever you are deriving the expression for bridge wave rectifiers, right? So substitution of 2RF wherever you find the RF values, right? So the efficiency is also same when you compare the center tap full wave rectifier with the bridge wave rectifier. Similarly, we have the ripple factor given by gamma, where gamma is equal to 1.21 for your half wave rectifier, and for the center tap full wave rectifier it is 0.483, and for the bridge wave rectifier it is 0.483. Similarly, the ripple or the output frequency would be equal to F for your half wave rectifier, but for your full wave rectifiers it is 2F. And similarly, the peak inverse voltage, that is PIV, peak inverse voltage, is equal to Vm for your half wave rectifier, and for the full wave rectifiers it is 2Vm. Similarly, we have studied the voltage regulation, which is given by Rf by RL into 100% is for the half wave rectifier, and for the full wave rectifier it is Rf by RL into 100%, that is for center tap rectifier, and for the bridge wave rectifier it is 2 Rf by RL into 100%. So wherever we find the Rf, we are substituting 2 Rf by RL into 100%. So hope this chart gives you an idea of the parameters with respect to half wave rectifier and the center tap full wave rectifier and the bridge wave rectifiers, which conveys you the various forms which conveys you the various parameters occurring across your half wave as well as the two full wave rectifiers that we have studied. So they should be in order to proceed with the problems, this chart is very much important, and knowing these formulas are very much important to proceed with the problems, guys. So I hope this video gives you an immense knowledge on the rectifiers, and hope this would be a beneficiary video for you. Thank you.